All right, hello everybody and welcome back to Linear Algebra Online. So the plan for today is to talk about something called subspaces, and subspaces are really important in linear algebra. I think actually in the textbook it starts off and says that this section is maybe one of the most important in the whole book, and I think that's kind of true. Definitely an important one to make sure you know. So to start off, I'm going to kind of pose this interesting question. So if you have a plane through the origin in R3, basically it's going to look like a copy of R2. So what I want you to think about is, are the vectors in this plane 2 or 3-dimensional objects? So like the first kind of stance you could take is that the vectors are 3D because they have 3 components, right? But the other idea is like the vectors can be written as a linear combination of just 2 vectors, so they are 2-dimensional objects, right? And this is like honestly at its core, like so much of what we're building up to in linear algebra. There's going to be something you're going to learn about way down the line, but there's something called an isomorphism. And an isomorphism is basically a map between 2 vector spaces, okay? So like maybe you have vector space V and W, and these can be all sorts of different things, and we're going to talk about what it means to be a vector space and all that sort of stuff later on. But basically, if we can create this special map that goes from this space to this space, then we can actually just work with either one, and basically the properties sort of transfer. There's going to be a lot of things where we say they're invariant in this isomorphism, so they get transferred nicely. It basically is a mathematical way to say that this space is identical to this space. And even though the vectors are 3D, like they have 3 components, in this problem, we could actually make an isomorphism between the plane through the origin R3 and R2. And that the formalism in being able to do that is at its key. The first step to understanding that, I guess I should say, the key is subspaces and knowing what a subspace is. So before we can get here, which is literally months down the line, we need to understand what I'm going to talk about today. All right, so what is a subspace? So a subspace is basically just something that any collection of vectors that satisfy these 3 things. So the collection of those vectors need to have the 0 vector in them, and then any 2 arbitrary vectors in that set, okay, their sum needs to be in there as well. Okay, and that's what we call being closed under addition. And then if you have some arbitrary vector in S and some sort of scalar, okay, then C times that vector needs to be an S. So S is closed under scalar multiplication. Little bit beyond the scope of our class 2 right now, but basically C, that scalar there, just needs to come from what we call the field that we're in. So here we're saying Rn, but it could be like the complex plane, or it could even be other things there that are even weirder. But basically those are like the fields that we're working with. So we're saying that like some scalar, some real number in this case, but honestly there's other problems where that could be something else. But so if you think about what properties 2 and 3 say, they're basically saying that you need to have any linear combo of U and V in S, okay? And what this basically is going to do is it's going to give us lines, planes, like it could even be like higher dimensional, like volume, kind of space, like 3-dimensional space. But any of those things where it cuts through the origin is going to basically be a subspace. And the origin part is important for a lot of like linear algebra properties, you need this zero vector to be able to do certain things. So it's an important part of what we call this thing a subspace. So along those lines, I want to show that every line and plane through the origin in R3 is a subspace of R3. All right? And so if it's through the origin in R3, then this one's basically good because the zero vector is in my set, okay? And then for the second condition, okay, we're going to say like let some arbitrary u and v be in the like line or plane. And we need to show that u plus v is in the like line or plane. So go ahead and I'm just going to sketch this for a line first. So, for the line, basically if it goes through the origin, right, this like vector, we'll use u because I'm using u down there. U would equal like the zero vector because it's the origin plus some scalar times like a direction vector, right? And so that means that if u and v fit this, then, basically we have u plus v, and we have like u is t times that direction vector, and then v just is some other scalar like s times that direction vector. And then you could add, basically you take out the d, right? And this thing has the structure of a line still, right? This is still a line in S. So I'm actually gonna kind of ignore this for a second. I'll get back to that. This means that for lines we satisfy the second condition, okay? And then for like a plane, right, I'm just going to do this up here, we would have like some u equals like the zero vector plus like td plus s d1 or something d2. And it's just like the vector form of a plane where those are like direction vectors. And basically the proof is like the same thing. If you do, here u plus v, then you would be inserting t d1 plus s d2. That's u, right? And then you're going to input, so I'll kind of group it. That's u, and then we'll have like, I'll just do p d1 plus q d2. And then it's the same kind of trick. We're going to group the d1s. We have t plus p times d1 plus s plus q times d2. And then this thing has planar structure. And not just any planar structure, but the specific direction vectors, right? So it's that specific plane. So u plus v is in S, right? And for the third condition, it's fairly similar, okay? So basically given u in S, we need to show c times u is in S as well. So I'll keep with the kind of colors here. So if you have, for u, right, c times u is going to equal to c times like td, but then you can just group your constants, right? And that's, check, it's good. It fits the same structure. And then for the plane, right, c times u would just equal c times TD1 plus SD2. And then it's the same exact trick. Group them. And group them. And again, I'm just going to do this. But the most important thing here is to honestly think about what this is saying. So it's basically just saying that, like, if you have, a 3D space right here, and there's some sort of like line that cuts through the origin, right? That if first off, it goes through the origin. That's like the first condition. The second condition is saying if you have a vector and then another vector in that line, that their sum is still in there, right? It's just gonna scale and get it like bigger, right? The resultant would just be, like somewhere out to like here-ish or so. And then the third condition is saying that if you have some arbitrary vector u and you scale it by like, say, 2, that vector is in there, right? That you never leave this line is the idea. So that line is sort of your world, if you want to think about it. And that actually goes back to this thing. This thing. And that's the most important thing to think about is if two spaces, like if something's going to be similar to like R2, then it needs to functionally have the same sort of like dimension and all those other properties that you're used to. A plane through the origin would do that. A plane through the origin looks like R2, and you can do the math in that plane the same way you can do the math in R2 proper. So like to me, having studied tons of math, I don't look at a plane as any different than R2. To me, they're identical because the math that you do in them is the same, and that's what linear algebra kind of goes ahead and shows you, which again, we're building up to. But this is a very important part to make sure you understand like the theory behind what we're doing. Okay, so this question, I just want you to show that, if every line and plane through the origin forms a subspace of R3, then justify why all vectors of this form, just like arbitrary x, y, z, that satisfy x equals 3y, z equals negative 2y, would form a subspace of R3. So what I'm going to start off with here is I'm just going to plug in my x, y, and z. So I'm going to have 3y, and then I'm just going to leave y as y, and then I'll have negative 2y for z. And then I can take like a y out, and I have 3, 1, negative 2. And basically what we're going to do is we're going to sort of think, let like t equals y, like parameterize this thing. And now you can just look at this as truly this thing is just a line. Whoops, I don't know why I was writing time. A line in the direction of that vector 3, 1, negative 2, right? And since every line and plane through the origin forms a subspace, then that thing is a subspace of R3, right? And geometrically, it truly is just this. Oh my gosh, it's truly this. It's just the line, through the origin, because like basically there is also this plus 0 vector going on right here. But it is a line through the origin, because there is, this plus 0 that's inherently there, and it's just going in that direction. That's geometrically what it is. So if I tweaked it just a bit, and I did x equals 3y plus 1, then the issue is it's going to change some things, because now I won't be able to get the 0 vector. So the 0 vector would not be an element of this subspace. That plus 1 is going to throw you off. So if this was how x was defined, then you would have to say this basically does not form a subspace. all right? And it's purely just this issue. 0 would not be in the set because of the 1. This is the bad thing right there. It's a bad arrow too. That 1 is the issue. All right. So just a little more generally, I wanted to kind of prove that, because what we've been kind of tiptoeing around is that these with these lines and planes being subspaces, is that really like the span of vectors is a subspace, right? Because that's really all this is, right? This is a span of arbitrarily many vectors. This is one vector, the span, t times that direction vector is the span of d. A plane is just the span of two vectors, like d1, d2 here. And so it's reasonable to think that if you have arbitrary many vectors here, then the span of those vectors is some subspace of Rn. So just going to go through and check all these different conditions. So the first one we're going to check is that the 0 vector is in there. So 0 equals just like C1 V1 plus C2 V2 plus blah, 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 C K V K, right? Where C1 through all these different things is just 0, right? And that would do it. So you can just set all those different C's equal to 0, and you'll get the 0 vector. So that's good. So that's the first condition. So now I'm going to let like U equal this, and I'm going to let, like, say, V equal that, all right? And I'm going to do U plus V, which will equal that big messy thing. And then you've probably seen where this is going. I'm just going to basically group like terms. I got a C1 V1, D1 V1, so I'll group those, and so on and so on and so on. And what you would get is this. And that would then show that, this sum is a linear combination of the vectors, right? Because the scalars have now just, instead of being like C1, C2, blah, 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 there's C1 plus D1, and then C2 plus D2, and so on. So that is actually showing condition 2. And then for scalars, just note basically C times U would equal that thing, right? Which then if you just distribute, you would get that. And then the idea again is like the same. Now this is the span of these vectors, and you're just saying the constants are something a little different. But this shows that just like C times U is in the span of V1, V2, V3, blah, 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 up to Vk. So since we showed the 3 properties, then truly the span of like an arbitrarily large set is a subspace of Rn. All right, so the last 2 things I just want to do here, really important, honestly, and they're just special subspaces. So they are something called the row space and the column space. So the row space is denoted row of A, and the column space is col of A. And the row space of A is the subspace of Rn spanned by the rows of A. And the column space is subspace of R sub Rm that is spanned by the columns of A. And definitely look at the N and the M. It is important that you see it's like different, okay? Now, this definition never made like a ton of sense to me, I think, right off the bat, but I'm going to basically summarize really quickly here what this is saying. So the column space is basically just the, like it can be a line or a point or a plane or whatever, that you get after a transformation is done. So it's sort of the image of what the matrix does to that vector space, right? So like if the matrix crushes everything down to the x-axis, then the column space is the x-axis. It's just the result after the matrix transformation happens. And the row space is basically just the analog, but it's before you do the transformation. So think row space, think like domain, okay? So, and column space, think range, right? And actually when we write a matrix, like an n by n matrix, the amount of rows you got is actually related to where you end up, and the columns are where you start off with. Like when you, if you make a system of 3 equations like x, y, z or something, you have like a very specific amount of columns that each one represents an x, a y, a z. Which that kind of always was weird to me, that like the input stuff is kind of the second letter and the output stuff is the first. But column space, just the subspace that you get after a transformation, and the row space is the subspace you get before you do the transformation, okay? And so basically in a question like this, all right, if you have a vector and you're asked, is it in the column space of this matrix, all right, you are basically being asked, is B in the span of A? All right, which we've done. We've done this question. And all you have to do is be like, okay, I'm going to make a matrix, augment it with 1, 2, 3, and then I'm going to RREF the thing, and I'm going to get, in this case, you get 1, 0, 3, 0, 1, 2, and then a row of zeros. And since this thing like has a solution, then yes, B is in the row space, sorry, we're doing columns, is in the column space of A, right? And that's it. Basically, we can do this matrix transformation, and the vector 1, 2, 3 is somewhere in the like subspace of the effect of that matrix, if that makes sense. And to do the row space, it's very similar, and I think I did it on the next slide. Yep. All right, so to determine whether W, which equals 4, 5, is in the row space of A, I'm going to do this a little bit differently. So you actually could take A, I don't like that color. You could take A, and you actually could augment it like down here. It's okay to do also, and like solve it out from there. And that's like in the book, and you can read about it. But it's actually going to be important that you know that you can do it this other way as well. So it shouldn't be that hard to believe that W in the like row space of A happens like if and only if the transpose of W is in the column space of A, right? And this is like where we're going to start seeing a lot of nice back and forth between like rows and columns. So this notion of the transpose lets us sort of flip-flop things, and we just need to change our understanding. So we can change from row space of A to column space of A if we're working with the transpose. So what I'm going to do is so the transpose of T is, well, let me back up a little bit. Transpose of T augmented with W is what I'm going to write here. And we would get 1, -1, 0, 1, 3, -3, and then 4, 5. And we're basically just doing the exact same computation that we did before. We're going to RRAF this thing because we're doing a column space again, even though we're going to interpret it as a row space. And so if you do the RREF here, you get this thing. And this again, this bottom row, I mean, there's actually infinitely many solutions this time. And it shouldn't actually be surprising that it's infinitely many solutions, because we have, like, if we think of these, these are two-dimensional vectors, like an x and a y, we have three of these things, which, unless you had three that were completely just linear combination or scalar multiples of each other, then you should definitely be able to span all of R2. So actually every vector of R2 is showing up somewhere, and that's related to the fact that we're getting infinitely many solutions here. All right. So, I guess I just answered this question. So I wanted you to also think about describing these things geometrically, and because we're really getting infinitely many solutions here, or you can just interpret it as you have three non-scalar multiple, like three linearly independent vectors in R2, then you have to be spanning all of R2, right? So the row space geometrically is R2, right? And likewise, if we go back and think of the column space problem, okay, we found out that this is in the column space, so it's in the space you get after this transformation happens, okay? And there's a very important result and we've been talking about this, that, when we see a matrix A, like 1, 0, 3, negative 1, 1, negative 3, this represents where I hat is going to land, and this represents where J hat's going to land, okay? And so you can just take those vectors as your direction vectors, right? And so the column space of A, to interpret it geometrically, is just a plane in R3, because it's got three inputs, right? Through the origin. It's kind of a given because it's a subspace. And it has direction vectors, basically just 1, 0, 3, and negative 1, 1, negative 3. And that is about it. So that's the most important kind of stuff that I want to make sure that you understand for today.